Okay, well, my goal today, I don't know if I can make it because the questions do take a bit of time, is to try and finish 16.3. So give you a heads up of where it is. What you're looking at here is a vector function where we call this guy P and we call this guy Q, and both of them are functions of X and Y typically. And it's a conservative field, which is, sorry, I'll take the mute just to save some background sounds. Right, and let's return. So, if you have a function f, it's made up of two components, p and q. Both are functions of x and y, at least typically they are. It's called the conservative field if the partial derivative of the first guy is equal to the partial derivative of the second guy, but the first guy with y and the second guy with x. Now, if it is a conservative field, and you have some curve C, maybe it's given parametrically from t equals a to t equals b, then we now have a short way of finding the line curve, the line integral. So the line integral over C of f dr is just basically little f of the position of the function at b, take away little f at the position of the function of a. And then the cool thing is that this little f, called the potential function, has the property that its gradient is f. So we basically do some integration to find this f. And once we know the potential function, we don't care how it gets from A to B. We only care about where it was at A, right? Its location at A. And we find its location at B, and we just subtract the value of the potential function at the end, take away the beginning. I don't think I mentioned this, so I'm putting it in now. Sometimes you'll see a line integral written down as f dr, which is pretty common. But you can also have it written down as grad f dot dr. You know that these are exactly the same. They're just two ways of saying it. It looks a little different, but they're the same. For the visual amongst you, which I am one of them, can you imagine that f of xy is this red vector field? And we're starting at P and we're traveling along this random kind of curve from P to Q. Then if I want to find the work done, which happens to be that line integral, then don't I only need to have the potential function f evaluated at the end, take away the potential function evaluated at the beginning, and it doesn't matter if it goes this way or if it went as a straight line or half a circle or any other shape in the world. The cool thing about the fundamental theorem of line integrals is, it doesn't matter. It just matters what the potential function is like at the end and at the start, and by subtracting them. So that's kind of an overview of where we are. So what we're going to focus on now are some more examples. Yeah. Lots of examples, we get better. So I have a function x cubed, y cubed. I think they use phrases like the path. So they're not telling you what the equation is because it doesn't really matter. Technically speaking, we should check these out to make sure that they're conservative fields, right? If the question doesn't bother to ask you, well, you just assume that it is, because it will be, right? Because if it wasn't, they wouldn't let you do the question because it wouldn't be fair, right? So technically speaking, you should check it. This is dead easy. That derivative is 0, that derivative is 0, they're equal, right? So it is conservative. So what we need to do is we need to find our little f. And the relationship we use is that one. And this guy is that fella. And I've decided today, at least on this question, to use this notation instead of df by dx, right? It's just, I don't want to get too caught up with one notation, then you don't realize that you can use others. So what have we got here? Well, we have that the partial derivative of f with respect to x is x cubed, and the partial derivative of y is y cubed. And essentially, don't we just integrate? Now, if you integrate this guy, you get 1/4 x to the 4 plus some unknown function, which we'll call our constant, g of y. And when you integrate this fellow with respect to y, you get that guy plus some unknown constant, which will be considered a function of x. And then don't you combine these two? And basically, this guy plus this guy. And so we now have our potential function. Well, if I've got its potential function, and I want to find the line integral, which is going to be the work, then it is going to be the value of the potential function, take away the value of the potential function, and where's it going to be? It's going to be from P to Q, right? Going from P to Q. So won't we evaluate it at 2, 3, and at 1, 1? Right. Position at the end, take away the position at the beginning. In this case, yikes, you're going to get 1/4 2 to the 4 plus 1/4 3 to the 4. Subtract, oh, that's a bit easier, 1/4 plus 1/4, which is 1/2. 2, 4, that's going to get me 4. That's going to get me 81/4. Take away 1/2. Guess that's what calculators are for. Let's find out. If I go 4 and I add 81/4 and I subtract 1/2, and then I just do math, first choice, and the answer's 95/4. Comfortable with that? It's a nice baby one just to get into the swing of things. Everything cool? Okay. Let's see what the next one's going to be. This one's like question 18. Here's our function. It's going to be the path from this point to that point. So all I need to do is find the potential function. Well, we have essentially two pieces of information. We know that guy. And we know that guy. Okay, what would this equal if you integrate it with respect to x?
X e to the negative y.
Great. Oh, I think that should be a plus, by the way. No, maybe it isn't. Let's keep it for a minute. I could be wrong. Now, plus some unknown constant, which we'll call g of y. Now we'll integrate this fella, and we'll integrate it with respect to y, which gives us a positive x e to negative y. That's why I thought I might have to change that, but I don't. Add some arbitrary function that could be in terms of x. In this case here, don't we get the same term in both cases? So that's it. We now have our potential function. To calculate this line integral then, we'll just evaluate the potential function at 1, 0, and we'll take away the value of the potential function at 0, 1. At 1, 0, you get 1 times e to negative 0, subtract nothing. Oh, the answer is 1. Right, e to the 0 is 1, and 1 times 1 is 1. Have you noticed how much, I'm trying to think of a good word here, simpler or straightforward using this technique is than if we had to do the parametric techniques from the other section, right? The one before this. And you can imagine that if it's a pathway, for instance, I guess the only thing you could do is probably do a straight line, but you know, in this case, we don't even need to know what it is. I think it's kind of cool. Of course, in the test, you're going to have to do both techniques. So when you're in the questions that want you to do it with parametric form and so on, you have to do it the old way. And then, well, one of the reasons you have to is that half those questions won't be conservative fields. And so if they're not conservative fields, aren't you stuck with the parametric way, right? You can't do anything else. But if they are conservative, you've got this one. What else I got? Oh, got this fella next. It's not written in a form that is kind of obvious what f is. But let me tell you how you get f. You get it from here and here. And you might be saying, well, what about the dx and the dy? Can you imagine me doing a dot product of these two things? Wouldn't you get this? Right. So if you ever get a dx dy version, will you just take the terms that have the dx next to it and think of them as your p, and the terms that are next to the dy, think of them as your q? Does that help? So I know that delta f is capital F. I know that the partial derivative with respect to x, comma, the partial derivative with respect to y is equal to 2x e to the y, 2x squared e to the y. So the first fella is him, and the second fella is him. If you integrate pausing here for a minute. If you integrate this guy, something not right here. Did I copy that down wrongly? Whoa, that isn't even question 8. See, I know that where this thing is going, that it's not the guy I wanted, and it has been done. There was a mistake. So let me rewrite 8 the right way. It's 2x e to the y dx, which is good. The mistake was here. So you might be saying, how did I know that I'd screwed up? Well, If you integrate this guy, don't you get x squared e to the y plus some unknown function of y? Can you see that doesn't play well with the other guy? And I knew it should have matched because they always match, right? So that's why I knew I screwed up. Okay, so pretend I'd never done that. And we're going to do C from 1, 0 to 0, 1. So that's going to be the path. And as if nothing happened, we'll start again. Right, so we're there. So the partial derivative with respect to x and y is equal to, that guy's like the p and this guy's like the q. So 2x e to negative y, and then a 2y taking an x squared e to negative y. Which better? So we'll match up first terms together. And then we'll match up second terms together. See how this, double check I haven't screwed up again. 2y minus x squared e y, that's good. 2x looks good. Okay. Well, if you integrate this with respect to x, basically you get an x squared with that guy, plus some constant in terms of y. If you do this fella, with respect to y, you get y squared. If you integrate this with respect to y, don't you get negative x squared e to the negative y times the negative 1, which gets you that guy. Now, do you see that they do match? So when you put these together, you're going to get an, oops, plus some unknown function of x, right? So you're going to get that guy and that guy. You're going to get 1 from here and 2 from there. Are we good? Okay, so you want the, I'll just call it FDR. You want this fella. Then evaluate the potential function at the end, evaluate the potential function at the beginning, and I've got a nasty feeling that we're not going to get too much out of this one. 0, 1, that's 1, and 1, 0, it's going to give me 1, get me 1. Oh, it's a nice answer.
Professor, Abigail
Yes.
got booted from class and she was asking to get back in.
I've let her in twice, so hopefully she's coming in, but thanks for telling me. She must be having issues. Now, this is an example of a 0. Now, don't you normally get a 0 if you start and finish at the same point, right? If it's a loop. But evidently you can get 0 other ways. Analogy. Can you imagine you go up a hill and then you go down the hill? Couldn't you be at 2 different locations, but the energy that you use to go up, you get it back theoretically on the way back? So I'm not worried about 0. It's kind of a nice answer to get. Positives and negatives happen as well. Anything about that, or is that question okay? Are we comfortable with the process now? Right. So I'm going to change the rules, and we're going to show you that guy. This is a 3-dimensional vector field. I am going to try and draw it, but imagine vectors in 3D, that more realistic, right? The world's 3D for the most part. We'll assume that this is a conservative field. You do not want to prove that it's one, trust me. There is a way of doing it, but it's really messy and really long. So we will assume by magic that it's okay. And we're being asked to find the potential function f. And then we're going to be asked to do this guy. And I have no idea what the rest of the question is. So I'm going to pretend it's from 1, 1, 1 to 0, 1, 2, right? Because we need a start and a finish, right? So let's get started. I know that delta f, right, the grad of f, is the vector function f. This guy has 3 pieces. And it's going to equal y squared z plus 2x z squared, then 2xy z, and then xy squared plus 2x squared z. And if you can't read it, it's the same guys over there. Now let's take each one slowly. This guy is going to be y squared z plus 2x z squared. Well, we're going to integrate it with respect to x. What will y squared z get you if you integrate it with respect to x?
Y squared zx.
Correct. If you integrate this with respect to x, won't you get x squared z squared? Now, the arbitrary constant is some unknown function that doesn't have an x in it. So fg, g of, I'll call it yz. It's really just a placeholder for the rest of the stuff, right? It really doesn't do much, right? It's just a placeholder. Well, I'll put a bubble around them. If we go to the second one, this guy is going to be 2xyz. And if you integrate him with respect to y, don't you get y squared cancels a 2, so you go x y squared z plus a constant that'll be a function that doesn't have a y in it. So we'll call it h of x z, right? It's just a placeholder. And that's as good as our second guy. Now we have the third one, which is x squared y squared plus 2x squared z. And if I integrate this guy with respect to z, you will get x y squared z. And integrate this with respect to z, you get x squared z squared. Great. Plus a constant that doesn't have z's in it, so fgh. I don't like I.
K.
Yeah, I like k. It's a placeholder, call it anything you like. xy. Now we put that package together. Shouldn't we be able to come up with what the potential function is? So basically, look at the bits and don't write them down if they happen more than once. Would you agree that that guy, and that guy are really just the same guy? So I know that one of the terms, and I'll do it alphabetical order, is that one. Would you also agree I've got a new guy that hasn't been used yet, x squared z squared? But isn't that the same as this x squared z squared? So I have an x squared z squared. And I guess that's taking care of that. What about this term here? Is there an x y squared z anywhere? Yeah, he's here, isn't he? So would you agree that when you combine them, these are the terms that belongs somewhere, at least within one of the three groups. You comfortable with that? Right, so there's F. Right, you want this guy? Potential function at the end. Take away the value of the potential function at the beginning. This is the potential function. So if we do a 0, 1, 2, that gets you 0. And if you do a 1, 1, 1, that gets you 2. So in this case, the answer would be -2. Can you imagine how ugly that would have been doing the parametric version? Even if we just made a straight line from there, it would still be big and ugly. I think I've sold this method as when it can be used as a very efficient way of getting line integrals. Now, what might they do to make your life difficult? Not much. Do you know, sometimes they might say, find the work done, in which case, calculate that. Sometimes they may say, find this guy, in which case, do the same thing. Right, it's not a different question. It'll still have an F. It'll still have a start and a finish. Well, we can get you sometimes on the start and finish. I've gave you pathways. So let me pretend that you had the same question, but I didn't give you a start and a finish. I gave you a space curve. And I told you that it was from t equals 1 to 2. Now, that space curve, the only job or the only use is to tell me these two guys. So don't you plug in t equals 1. And if t equals 1, you would get 1, 2, 1. That would be your start point, right? And if you plug in 2, that'd be 4. 4, 8. Can you see you now have your two guys that go here and here, and you've got your answer? Does that make sense? Right. In a 2D question, same kind of process. If they give you an r of t equals t cubed sine t, you know, and they tell you it's from 0 to pi, right, you plug in 0, you'll get 0, 0. If you plug in pi, you get pi cubed 0. And so there's your start and there's your finish guy. If it's 2D, you only get this with 2D. Can you imagine they tell you that it's, you know, the arc is y equals x cubed, and you're doing it from x equals 0 to 2? Right. When x is 0, y is 0, so that's your start point. When x is 2, y is 8, that's your finish point. You see, that's how you'd get your start and finish. Now, we don't care that it went through x cubed. We don't care it went through this space curve, and we don't care that it went through this space curve. Don't we only care about where does it start and where does it finish? Because in the line integral, it's the pathway doesn't matter, just the start and the finish matters. So don't get too caught up with this. Just use this to get a start and finish point, and that's it, done its job, right? It has, it doesn't take part in anything else. How are we doing? Any questions? Is this going smoother than parametric? Asked that last time. Still going smoother? Even the 3D one? Okay, well, here's another 3D one. Find F and get that guy. Oh, when they ask you for that guy, don't they mean that guy? Right, just in case you're thinking, oh God, what's this? It's nothing, it's that. All right, let's see what we have here. I know that delta f, the grad of f, has to equal the vector function. So fx, fy, fz has to equal yz, xz, and xy plus 6z. Right, so if you match the first one with the first term, we get that. Integrate with respect to x, you get x, y, z, and then fg, and then an arbitrary constant that doesn't have an x in it. So that's the placeholder for that guy. Move over to the second relationship. A lot of deja vu happening here. Would you agree that's the integral? Plus a constant that doesn't have an x, doesn't have a y in it. That's our second guy. See what the z has. He has an x, y, plus a 6z. Well, at least we do something a little bit different. You get an x, y, z plus 3z squared plus some function that doesn't have a z in it. So we put this package together. Would you agree that they all have an x, y, z? Anything else? Is that all there is to the potential function, or is there another term?
There's still that 3z squared.
Are we comfortable about how you take each of them and you stick them together? Right. And so now I know this guy. Can't I basically just go over here and say the potential function at 411, take away the potential function at 1, 2, 3. Right, if you evaluate this at 411, it's going to go here. So what does that look like? It's 4 times 1 times 1 plus 3 lots of 1 squared. And then if you evaluate it at 1, 2, 3, you get 1 times 2 times 3 plus 3 lots of 3 squared. 4 add 3 is 7. Take away 6 add 27 is 33. It looks like in this case you get negative 26. Any questions, or we're still got that nice flow? Would you agree it's just got a flow to it? I wouldn't even say the integrations are particularly bad. I mean, they're power rules for the most part. Right, now, why don't you lot say hi for a moment? And that'll give me a chance to just quickly look at the homework, and I have to get these answer things out of the way because they distract the heck out of me. Right, you all saying hi, hopefully? Looks like you have. And I will now go and we'll have a little look at what the homework looks like. Well, here's a weird one to start with. Figure C shows a curve C in a contour map of the function f, whose gradient is continuous. Find the integral C delta f dot r. That's just the same as our FDR kind of guy, right? They took the vector field and made a gradient field out of it. So somehow or other, and don't overthink this, shouldn't it be the potential function at the end take away the potential function at the start? What's the potential function's value at the end?
60.
And then 20 at the beginning? So can you imagine the answer is 40? Which it is. So there wasn't any cool, weird math there. It was really understanding that they gave you a kind of another way of looking at the expression. What does that look like? Check if it's a conservative field. I think that's pretty obvious. Good. Don't you differentiate that with respect to y and differentiate this fella with respect to x? And then if it is, you can then find the potential function f. Right? And if it's not, then you are meant to write in capitals dne. Can anybody tell me, is this a particular one, is it a conservative field or not?
No, it isn't.
Right, correct. One of the derivatives, well, they're not equal to each other. Obviously, one is not the same as the other. In this one here, you can see a pathway that goes this way. You can see a pathway that goes this way, and then you've decided, I guess, to do a sinusoidal curve that goes this way. This is the vector function. Can you see that's a start point and that's an end point? Can we assume that this is a conservative field? And then calculate it. Oh, actually, I know what the answer is. No, well, I'll let you figure it out. There's a 3D one. C to there. Now they're calling it a line segment, which is fine. Do I need to calculate the equation of the line joining those 2 points to answer this question? No. So, I mean, it's nice to tell me that, but it doesn't matter. Couldn't I have just said the path from one to the other and just, we've got a start and a finish coordinate, we're good to go. In this question here, can you see that the start and finish point, you will get it from here? A bit bigger. Can you see that this is the curve, but at 0, the curve has position 0, 6, 0, and at 1, it has position 1, 7, 1, right? So that's your start and finish coordinates. And then don't you just do the usual delta f equals f and solve for the potential function? And there's one of those dx dy's that I did. That's the correct version of 8, not the first one, but the second. Here's a work done question. So when you see a work done, won't you just find the integral of f dr? The same way we're doing everything else. They don't say it, but we know that's what you do, right? Determine whether or not this is a conservative field. And if it's not, just say dne. Here's another one, check if it is or not. Is 11 a conservative field?
Yes.
Yeah.
Correct. If you differentiate this first piece, which basically is your p, if you differentiate that with respect to y, don't you get e to the x cosine y? And if you differentiate this with respect to x, don't you also get e to the x cosine y? And that's all they want to know. Well, that part. And then don't you just find the potential function little f the usual way? Similar question. Scanning through these. Ooh. I think I should do 14. Yep, we got time. This is going to be my last question. So hopefully by the end of this, I'll have covered enough situations that you'll feel comfortable about whatever's left. So I'm going to do a version of 14. We have this guy. It's the log of y plus 18 xy cubed. And then, good grief, 27 x squared y squared plus x over y. That better be a conservative field. I do not want to do all this work to find out the answer is DNA, because that would not be a good finish to today. Okay. So let's check it. Give it some letters. Right, isn't that your P of xy? Isn't that your Q of xy? So if I do a partial derivative of this guy with respect to y, and I do a partial derivative of the second one with respect to x, they better be the same. With respect to y, you get 1 over y. And if you differentiate this with respect to y, you get a power rule, and you get 56x y squared. If you take this guy and differentiate him with respect to x, you get 56x y squared. And if you differentiate this guy with respect to x, good news, it is a conservative field. Okay, so now I'm going to try and find the potential function by solving that situation. Pretty messy, right? The first one is the log of y plus 18xy cubed. Well, if you integrate with respect to x, you stick an x in front of that. And don't you add 1 to the power and divide by the new power? So I believe that's what you get. Plus some function doesn't have an x in it. We take second one now. And we integrate this fella with respect to y. You add 1 to the power, divide by the new power, and I think you get 9 x squared y cubed, which is good news. Okay, be a little bit careful. What is x over y when you integrate it with respect to y?
X natural log of y.
Agreed. And perfect match. Oops, but just for completeness sake, right, do that guy. And so we now have a potential function. It has 2 pieces to it. In this particular example, don't both of them have both pieces, but that doesn't need to be true every time. I got a potential function. I guess that's it. There wasn't a second part of that. It's a pity because couldn't you have done a start at 1, 2 and finish at 5, 6 or something and actually, you know, do the whole line integral thing? But yeah, it is what it is.